Hello, hello, hello. In this worked example, I'm going to go through a few examples that will serve as an introduction to the work kinetic energy theorem, which is discussed and derived in the Wolfson text, Wolfson chapter 6. So I'm going to assume that you've read chapter 6 carefully, and this is just meant to complement the part of chapter 6 that deals with the work kinetic energy theorem. So let's dig in. So in a previous episode of What's the Big Idea, we talked about the energy principle, which we could describe this way. We have some system in the world, uh, and the system in general can be anything, and we separate the world into the system. Everything inside the dotted lines is part of the system, and everything outside the dotted lines is part of the surroundings. And then the energy principle introduces this idea that you can calculate, you can define this quantity called the energy of the system, and you can calculate how the energy of the system changes by calculating the amount of work done on the system by the surroundings. And of course, we need to define what we mean by energy and what we mean by work in order to make any sense of this. But this ends up being a very general and far-reaching principle. And to begin to approach this energy principle, we're going to take a special case. We're going to take, as physicists are often want to do, you start with a very, very simple system, and you try to explain what the energy principle is like for that simplest possible system. And the simplest possible system that we're going to consider is a system consisting of a single particle of mass m. And by particle, we mean something that doesn't have any internal structure. It just is located at a single point in space, and all it has is a mass. And in that case, in that special case in which our system is just a point particle, uh, then uh, then in that case, the energy of the system consists entirely of kinetic energy of the point particle, and that kinetic energy is just defined as 1/2 mv squared, where v is the speed of the particle. And with that definition of kinetic energy, we can prove the following theorem. And by the proof, as Wolfson shows, is just really based on application of Newton's second law of motion. So the work kinetic energy theorem we can write as the change in the kinetic energy. So this is derived for a system consisting of a single point particle. So the energy of the system is just the kinetic energy of the particle. And so the energy principle says that the change in kinetic energy of the particle just is equal to the work done on it by the surroundings. And to make further sense of that, you have to then define what you mean by work. And work, you'll recall, is just by definition the scalar product. You have a force acting on the system, on the particle, and it undergoes a displacement delta r, and you just take the scalar product of the force and delta r, and that gives you the amount of work done by that force. So let's try to see how this works in practice by looking at a few simple examples. So as a simple example, imagine the following situation. There are two pucks, puck A and puck B, and they're different because puck B has 4 times the mass of puck A. And they're placed on some horizontal surface. This is a top view that we're looking down on. And there's some force that's applied to each of the pucks, and it's the same force, the same magnitude and direction force. And the pucks start off, and we assume they're both initially at rest at some starting line, and then they cross the finish line, not necessarily at the same time. But the question is, when they get to the finish line, how do their kinetic energies compare? Which has the greatest kinetic energy? And let you ponder that before we discuss the answer. So you should press pause on this video and think about what your answer is going to be, and we'll come back and see if your answer agrees with what I think the answer is. Yeah, okay, we're back. And which do you think? Is A have the greater kinetic energy, B, or are they the same? Those are the three possible choices. Well, from the work kinetic energy theorem, the final kinetic energy is just going to be equal to the work done on these particles by the surroundings. And that's because the initial kinetic energy was assumed to be zero. So the change in kinetic energy is just equal to the final kinetic energy. So in order to compare the final kinetic energies, we just have to compare the work done by the surroundings. And of course, the work is just F dot delta R. And if we look at our situation here, the F's are the same, and delta R is just a displacement. It's just a vector that goes from the start line to the finish line. So the delta R's are clearly the same. So it's obvious then that choice 3 is the answer. The final kinetic energies of the two pucks are going to be the same, even though this one, puck B, has 4 times the mass. So it's going to be moving slower, but its kinetic energy, 1/2 mv squared, is going to end up 1/2 4mv squared, rather, is going to end up being the same kinetic energy as puck A. Okay, one more simple example for you to ponder. This is a kind of convince your neighbor. Although, so if you have a neighbor that you're with, you can try to think about it and convince them of your answer. So, situation similar to the one before, where we've got a hockey puck sliding on some sort of horizontal surface, perhaps ice, and we observe that when it is starts off with a velocity of magnitude 1 meter per second, and then it hits a region in which there's some friction and significant slowing down occurs. And the puck, once it hits the carpeting, it travels for only a meter before it comes to rest. Okay, so that's an observation. And then the question is, suppose you had the same situation where you have a puck but you give it a different speed. You double its speed to 2 meters per second. How far along the carpet will it slide now? 5 different choices, and we'll pause for a minute. You should hit pause on the video, think about what you think, and we'll see you on the other side shortly. Okay, we're back. Well, to answer this, as you probably surmised, we're going to want to make use of the work kinetic energy theorem, which states that the change in the kinetic energy of the puck is just equal to the work done by the surroundings. So the change in kinetic energy of the puck is just the final kinetic energy minus the initial kinetic energy. And the final kinetic energy in the story is 0 because it's coming to rest. And that's equal to the work done by the surroundings. And the work done by the surroundings, there's going to be some frictional force, force of kinetic friction, times the magnitude of the displacement times the cosine of the angle between the frictional force and the displacement. Now, what is that angle? Well, the displacement is in this direction. The frictional force, the kinetic frictional force, points in the opposite direction. So the angle between the frictional force and delta R is 180 degrees. And of course, the cosine of 180 degrees is -1. So what we have from the work kinetic energy theorem is the minus signs, there are minus signs on either side of this equation. So we can get rid of the minus signs and we just write that the kinetic energy and is equal to the magnitude of the kinetic friction force times the magnitude of the displacement, which we can call d, the distance traveled. And our model of kinetic friction says that the kinetic friction really shouldn't vary between these two runs. After all, you've got the same surface involved, the same puck, so why would the frictional force vary? It doesn't depend, according to the model, on how fast the puck is going. So the FKs are the same. So this just says that the displacement, the distance it slides on the puck, is proportional to the initial kinetic energy. And in this story, between the two runs, we doubled the speed, but because the kinetic energy is proportional to the square of the speed, the kinetic energy actually quadrupled between the first run and the second run. So that means that in the second run, the puck should slide 4 times as far as in the first run. And in the first run, we were told it went a meter. So that means that in the second run, when it starts off at 2 meters per second, it's going to slide 4 times as far, or 4 meters. Now, this is actually pretty important for all you motorists out there. If you're driving a car, what it says is it's a pretty big effect. You only doubled the speed, but you quadrupled the stopping distance. And for motorists who are thinking about speeding, let this be a warning to you, because it means if you go twice as fast and you slam on the brakes, it's going to take you 4 times as long to stop. So this is why, and this is today's safety tip, if you're driving on the highway, don't speed. And if you are going to speed, leave plenty of room between you and the car in front of you, because it's going to take you, you're going to go a longer distance before you come to rest. So if the car in front of you slams on their brakes, it's going to take you a long time to come to rest. And I want you to all be careful and safe out there. So anyway, that's the end of this first introduction to the work kinetic energy theorem. Hope to see you again soon. Bye bye.